In this tutorial, we are going to learn how we can control an external LED using an Arduino UNO and NI LabVIEW Community Edition. What we have in front of us right here is an Arduino UNO. To it is connected a green LED. In series with this LED is connected a fixed value resistor, and this resistor is connected to a digital pin on the Arduino UNO. In this tutorial, we are going to learn two main things. First of all, what's an LED and how we can size the fixed value resistor connected in series with it. Second, how we can write an NI LabVIEW code in order to control such an LED. First of all, let us go ahead and check what are the hardware components needed for this tutorial. We need an Arduino UNO R3, fixed value resistors, a power source to power up our Arduino UNO and LED, a breadboard on which we will assemble our circuit and electronic components, along with some wires to connect our electronic components, a USB cable to connect our Arduino UNO to our PC or laptop, and finally some LEDs with different colors. Now for the color of the LED, you can choose any color that you like. However, we need to size the fixed value resistor depending on the color of the LED, as we will see in a bit. In terms of software, we are going to use, as stated earlier, the NI LabVIEW Community Edition. Now the question is, what's an LED? A light-emitting diode is a semiconductor device that emits light when current flows through it. And since it's a diode, it means it passes current only in one direction. This means that we need to hook it up to our circuit in the correct way in order for it to operate successfully. This is an LED. Usually an LED has two terminals, a positive terminal and a negative terminal. The positive terminal is the long leg of the LED and it's called the anode. The negative terminal is the short leg of the LED and it's called the cathode. The positive terminal should be connected to the positive side of the power source, and the negative terminal should be connected to the negative side or the ground of our circuit in order for our LED to work properly. Now, in case the two legs of the LED are of equal lengths, we can distinguish them using the flat edge on the LED that indicates that this is the cathode's side. An LED has what we call a forward voltage, and each LED has a different forward voltage depending on its current, along with a required amount of current that needs to pass through it. It's very important to note here that the amount of current for each LED should not be surpassed, otherwise the LED will be damaged. So this is why we need to size our fixed value resistor in order for our LED to operate properly and safely. As you can see here, we have different LED colors with typical forward voltages. For example, a red LED has a forward voltage between 1.8 and 2.1 volts. A yellow LED has a forward voltage between 1.9 and 2.2 volts. A green LED has a forward voltage between 2.0 volts and 3.1 volts. So as you can see, the forward voltage depends on the color of the LED. And we need to make sure that this voltage is supplied to the LED for it to shine. The question here is, how can we size the value of the fixed resistor in order for our LED to operate safely and successfully? If we have, for example, a green LED, which has a typical voltage between 2.0 and 3.1 volts, and here we will take specifically 2.2 volts with a required current of 20 milliamps, what we have here is a circuit in which the LED and the resistor are in series. And since we know the voltage drop of the LED, which is 2.2 volts, which is its voltage drop, and we know that the current that passes through the LED and the resistor is the same, we can simply use Ohm's law. And based on Ohm's law, we know that the resistor value is simply the voltage of the battery minus the voltage of the LED divided by the current that passes through the elements, which is 20 milliamps. In this case, we have 5 minus 2.2 over 20 milliamps or 0.02 amperes, and this value is simply 140 ohms. So the fixed value of the resistor that ensures a safe and successful operation is 140 ohms. Now, to be on the safe side, we should take a slightly larger value. In this case, we will opt for a 220 ohms resistor. Now, it is important to note here that the higher the value of the resistor here, the dimmer the LED will be. So if you increase it too much, you will see a dimmed LED. So it's important to note that. This is the circuit schematic and the hookup circuit diagram for our LED. So as you can see right here, we have the Arduino UNO. The negative side of the LED is connected to the ground pin, and the positive side is connected in series with the resistor to the digital pin on the Arduino UNO. And this digital pin in this case is pin 13. And this is the circuit schematic. So we know that the digital pin is connected internally to the ground of the Arduino UNO, and the digital pin is connected to the 220 ohms resistor in series the LED. And as you can see, the symbol of the LED is a diode with two outward arrows, which means it's a light emitting diode. And the LED in its turn is connected to the ground. Again, the resistor here is a 220 ohms resistor since we have chosen a conservative value. Now let us go ahead to LabVIEW and see how we can control our LED. In other words, how we can turn it on and off and blink it as well. So I'm going to go ahead to LabVIEW, open an empty VI that I have already created. So for your case, you can create a new VI. I'm going to place my block diagram on one side and my front panel on the other side. Next, what we are going to do, we are going to Hobbyist, Library. We are going to choose the open block and the closed block in order to open or establish the connection between NI LabVIEW and MyRio, and the close in order to close it once we stop our code. For peripherals, we're going to digital, and for that we're going to choose the right digital output, since we want to either send a digital high, which is 5 volts to our LED for it to turn on, or digital low, which is 0 volts in order to turn it off. Now what we can do, we can place our digital right block inside a while loop, connect the blocks together using the data line and the error line, and for our open, we need to choose the COM port that our Arduino UNO is connected to. In this case, it's COM4 for my case. Then for our digital write block, we will choose pin 13, since this is the pin that our block is connected to. And for sending digital high or low, we are going to go with a silver style push button. So we'll call it LED control, and we'll connect it to our block right here. Perfect. Now what we need is we need a stop button in order to be able to explicitly stop our code. We're going to hide the label and connect it. However, in case we have an error, we need to stop our code. This is why we need to monitor the status of the error line. And if we have an error, we need to stop the code. So our code will be stopped either using the stop button or if we have an error. This is why we will choose to have here an OR gate. And if you would like to display the label, you can display the label of your gate by choosing visible items. Perfect. This is all what we need. What's left is just to have a virtual LED right here in order just to display the status of our physical LED virtually. So our code is ready, but there are one minor thing, which is our general error handler. we can place it there, and here on its output you have different functionalities. You can have an LED to show you whether you have an error or not. You can display the message and other things. So please go ahead and explore them yourself. Now let us go to our physical LED, place it on one side, our block front panel on the other side, and run our code. As you can see here, whenever I turn on or press the push button, the virtual push button, our LED turns on. Whenever we release it, our LED turns off. And now we have full control over it. Now there's something very important that you should remember, that I have already uploaded the firmware wizard. In case you haven't, you have to upload it again as we did in our first video. So we can choose the COM port, we just click next and upload it, and you will see your LED, embedded LEDs flashing, indicating that it was uploaded successfully. Now you will see here the green LED flashing because it's connected to the pin 13, and we know from tutorial number 1 that pin 13 is used to control the embedded LED. So we can run our code again and make sure it's running smoothly. Now there's one major issue with this code. If I turn on my LED and I stop my code, my LED remains on. And this is something not practical, and we need to turn it off whenever our code stops. So it's a common practice to have a digital block right here outside of our while loop. So we can simply copy our digital block code, and we can specify the same pin as well, which is pin 13. And here we can have a constant, and this constant is simply a false constant that we are feeding to our digital pin 13. So we send digital low or 0 volts in order to turn our LED off whenever our code stops. Okay, so let's see if we can just put it right there neatly. So it seems like perhaps this is better. Let's now run our code and see what's the difference. Whenever we run it right now, I can turn it again on and off, but even if it's on, whenever I stop my code, I can see that it will turn off automatically. And this should be a common practice in your codes. Now, another thing we are going to talk about right here is how we can flash our LED or blink it. So let us go ahead and delete the connection here between our LED controller and the digital output value of the block, and let us go ahead and choose here the elapsed time block. Now this elapsed time block allows us or measures the time elapsed when the code starts running. And here I have two options. I can either reset the elapsed time after a certain time target, in this case it's 1 second, or I can just keep monitoring the time as it progresses. So for us right here, what we are going to do, we are going to automatically reset after the time target is achieved. In other words, what will happen here is that after 1 second, this timer will go back to 0 and count to 1 second again. And you can choose this value either from here or programmatically from outside this express block. So let us keep it here to 1 second, and let us see how we can use this block in order to change or flash our LED. So what we can do right here is the following. We can have two controllers right here, pneumatic controllers. So the first one, we call it threshold time in seconds. And the second one, we will call it time target in seconds. Since we can change these two, then we're going to place them right there, distribute them vertically. We'll have our stop button right there, and our time targets right there. Now, here's what we are going to do. We are going to use the comparison palette, And specifically, we are going to use the less than or equal. And we are going to monitor the elapsed time. And if the elapsed time is less than or equal to a certain threshold value, what we are going to do, we are going to have a digital or a true value right here at the output of this comparison. And we will send this value to our digital write block. And if our value or our elapsed time here is higher than this threshold value, we'll have a false constant right here, and we will send also this false constant to our digital write block. And in this way, we are sending high and low depending on whether we are below this threshold value or above it. So let us go ahead and connect this value to our block. Let us move it a little bit. Okay, backward, put it right there, and connect our LED to it. Now for the time target right here, we can also connect our pneumatic controller to it and choose which time target do we like. So let us go ahead and try to test this code. So let us minimize our block diagram and let us run our code right here. First of all, let us say we want to turn on our LED for 0.5 seconds and turn it off for another 0.5 seconds. What we can do, we can set our time target to 1 and our threshold value to 0.5. And you will see here that our physical and virtual LEDs, they will both turn on for 0.5 seconds or 500 milliseconds and off for another 500 milliseconds. Now, if I want them to be on and off for 1 second on and 1 second off, we can just put 2 here and 1 for the threshold, and you will see that we can change that. If I need a faster flashing, we can go for 0.5 seconds with 0.25 right here, and you can see that it will flash much faster. If you want unequal amounts, I can simply set the threshold value, let's say here, to 100 milliseconds. Then my LED will turn off for 0.4 seconds and on for 0.1 milliseconds, or I can do the opposite, just put here 0.4 to flip the timings. And this is how you can flash your LED. So for example, here I can have 1 second and I can have 0.9 seconds of an on time or 0.1 for the on time to have a blinking LED. Now, one more thing to note in our block diagram, that this code can be rendered more efficient by just having a timing block right here with a duration of perhaps 10 milliseconds. This will make sure that our while loop runs smoothly. So we don't need really a very fast while loop, and everything will work just exactly the same. And this is it. So let us just make our block a little bit neater. And this is our whole block diagram. So let us see it one more time. So we can have our LED 0.5 seconds and a threshold value of 0.25 seconds. And we can zoom in. And as you can see, we have a functional LED that is controlled using an Arduino UNO along with NI LabVIEW. And this is it for this tutorial.